Hey folks, so I'm going to keep things pretty short this week, partly because my computer broke over the weekend and I had to go get a new one, and I'm a little bit behind after having to set up a new system. But anyway, also, you all are quite busy with Lab 3, which I recognize is very involved compared to the other two labs you've done so far. So I'm actually going to extend the deadline for Lab 3 to Friday just to give folks a little bit more time to work on it. Also would like to say that Lab 4 is not going to be as arduous. For Lab 4, we're going to get a bit of an introduction into web mapping and also learn how to do geocoding, where you take addresses and turn them into coordinates. But it will be a little bit more hands-off than the Lab 3 at least. So yeah, I'm going to push back the deadline for Lab 3 to Friday. I'm also probably going to push back the date that I post Lab 4 just because I have a bit more work to do with it. But for today, I'm just going to cover a couple things. I'm going to introduce some raster overlay methods, show you some techniques that you can use to like analyze terrain, do some slope analysis to identify a good spot for a ski resort, and show you how you could do some aspects of the tsunami risk assessment using raster overlay instead of vector overlay. Vector overlay being the things that you're doing in your model for Lab 3. So I'm going to introduce a little bit of that, and then I'm just going to take a few moments to talk about and introduce the final project. I'm not going to post the full details yet or anything. You don't have anything to do for that immediately. I just want to make folks aware of it. And since this is a really abbreviated summer term, I want to give you as much time as possible to think about it. So with that said, I'm just going to open up Arc. So I just want to show you two different kind of sets of analysis that you could do with some raster data, some things that might give you ideas for techniques you might want to use in your final project, and also just show you the other side of things because we focused mostly on vector data so far. So I have here the DEM that you're working with in Lab 3. So it's the Port Alberni DEM digital elevation model for the central portion of Vancouver Island. And then I also have here a roads layer. This is just highways, arterial roads, and freeways. And so we have a question. Where's a good spot to put a ski resort? There's a couple things that we might need to answer to address that question. So first, let's say we have a criteria where we need to be within like 10 or 15 kilometers of one of these roadways. So we can buffer the roads layer and convert it to a raster layer, and then do a bunch of analysis along with the terrain. So there's a handful of criteria that we need to meet to do the terrain analysis for a ski resort. So I've just created a model here to sort of highlight how one might go through this process, and I'll just show you the different outputs along the way. So you've gotten an introduction to Model Builder so far in Lab 3. Models are really useful because they help you visualize your workflow. And so more broadly speaking, flowcharts, which is essentially the way this model is laid out, are really nice because they can help you understand and visualize the flow of information. So I'm actually going to have a question on the final exam where you have to draw a flowchart similar to like how you would set up a model. So we have a question. Where's a good place to put a ski resort somewhere near Port Alberni? We've got a handful of criteria. You need to be high enough elevation to where there's actually going to be snow. We want to look at the angle that the slope is facing to see, is it a south-facing slope or is it, perhaps a more shaded north, east, or west-facing slope? South-facing slopes, get more direct sunlight, so they're not as ideal depending on the elevation. They can impact snow conditions. And then we also want to know what's the slope of the terrain. Is it pretty flat? Is it ideal for skiing, or is it too steep, in which case it's going to be dangerous? So some of the tools that we're using here in this model, you've already worked with before. So what I did was I buffered the roads layer by 10 kilometers. And then where in lab 3, we took a raster layer and converted it to a vector layer and then did a bunch of vector overlay. Here I'm using the Polygon to raster tool, which is just the opposite, to create a vector layer. So we've got this roads buffer, and then we've got the rasterized version of it. So if you buffer the roads layer, this is the vector that you get, and then we can convert it to a raster using this function. And the only choice you really need to make is, one, you can, when you're buffering, I've selected the dissolve type, dissolve all outputs, so it just creates one shape. This is all one shape, and if we open the attribute table, we see that it's got an object ID value of 1. So it's just going to set the object ID value as the, what's called the value field. And so that's going to say anywhere where the roads buffer exists, it'll create a raster with a value of 1. And anywhere without it, it's going to say no data. So no data is a nice way to filter things out. So I've created this roads layer. I've converted the vector data into raster data. Now we can meet the other criteria. So first, we're just going to take the elevation layer and bring it in 3 separate times because we want to look at the slope, the aspect, and just the elevation. So we can reclassify the elevation, for instance. And so I've just done 3 criteria here. We'll say, okay, if it's below 600 meters, it's not going to get enough snow to be feasible. Between 600 and 750, it's going to be marginal, maybe. And then 750 to 1,000, it'll be good. And anything above 1,000 meters, we can say, okay, they're going to have a long snow season. So we'll give it 0, 1, and 2. So we can rank them. You can. One of the nice things about Raster Overlay is you can create rankings and like suitability criteria. And so rather than with vector layers where you just do an intersect and it's like this is where they overlap, you can get gradations and scales and things to help sort of weight your outputs. So we reclassify the elevation, and then we're going to look, and we're going to use this tool called the aspect. And we'll take, what the aspect does is it just calculates the direction that a slope is facing. So I've run the aspect here, and we'll just take a look at the output to see what it is. So if you look at the aspect, basically it comes up with all these different values. It says flat for things like water, and then it'll tell you north, south, east, west, and so it automatically classifies it for us, but it just outputs as these degree values. And so the only thing that we're interested in here is it south-facing or not? And so I've added into the model a reclassify of the aspect, where we just say, okay, if it's between 160 degrees and 200 degrees, so that's approximately south facing, we'll give it a value of 0 and say, this doesn't add anything to the snow suitability. If it's not, if it's in any other direction, we give it a 1. And then we can use this tool called the Raster Calculator, which does exactly what it says. So we'll just take the Raster Calculator, and you can use this thing to do simple algebraic expressions. So for instance, I'm just adding this layer to this layer. So this input, which is the reclassified elevation, and this input, which is the reclassified aspect. And I will add them together to create a snow suitability score. So we can just look at what this creates. And so for this, essentially, anything above 0 is good. A value of 0 is like not going to be good. That's a low elevation, and or it's above 600 because we said anything below 600 meters is just no data. So none of this is suitable. But if we have an elevation of 600 to 700, it is suitable if it's not a north-facing or south-facing slope. So anyway, basically, we've created this snow suitability score where 3 is the highest and below 1 is not acceptable. So you can do simple functions like just adding 2 things together. Now our other criteria is the slope. So we can create this, we can use what's called the slope tool, right? And so you can find slope or aspect just by quickly searching in the geoprocessing pane. And to run the slope tool, there's really no choices you have to make. You just leave all the defaults as is. This Z factor will exaggerate things. So if for some reason you want a really high value, type in 2, 3, whatever. Basically, just leave it all the same. What the slope tool is going to do, we'll just see the output of this one. It's going to show us the steepness of the slope in angles. And so we can see that like there's not much above 45 degrees, but it provides pretty good resolution. And so our criteria, we're going to reclassify it and say, okay, anywhere that has a slope of 0 to 10, like, all right, that's going to be okay. Anywhere from 10 to 30 is going to be ideal. 30 to 55 is going to be okay. And then anything above 55 is going to be dangerous. So we'll give it a -1. So you can use the raster calculator to add, in which case you'll like set up scores that are cumulative. Or you can use it to multiply, which can, you know, if you multiply a value by 2, that's going to give it more of a rank. Or if you multiply it by -1, it's going to create a negative value. It's going to say, like, turn it off, essentially. So we can use the raster calculator additionally to just multiply multiple layers together. So we've got the roads buffer, which is just 1 or no data. We've got the slope, which is ranked 1, 2, or -1. And then we've got the snow suitability. And so we can just multiply all these together. And our final output will be something that looks like this. So we can say that these light blue are marginal. And so if I go to the symbology, you can see how I've classified these things. Right, and so anything with a value below 0, that was the slopes that were above 55 degrees, gets coded as a negative value. So we can say anything below 0 is danger. And so you don't want to plan to put anything there. And then anything with a low value is anything above 0, but a low value can be marginal, and then suitable, and then ideal slopes are, again, the best conditions. And so you can use the raster calculator and the raster overlay to do some pretty complicated chains of analysis and overlays, and the flexibility that is added by like being able to rank things can sometimes outweigh the downsides of the increased computational time for doing things with raster data versus vector data. So another circumstance we might want to use raster overlay instead of vector overlay could be to repeat the tsunami risk assessment for Port Alberti. So here's just a simplified look at things. Again, I've got the DEM and the water bodies layer. And so in lab, what we did is we set an elevation threshold, and then we reclassified it and converted it to a vector. And then we did the rest of the analysis. But what if we want to look at multiple different scenarios? What if we want to say, like, small tsunami, medium tsunami, and like catastrophic? So we can look at multiple elevation thresholds using raster overlay, and we can rank or create multiple different scenarios. So for instance, we can do a variable ring buffer around the water bodies to look at, say, 500 meters, 1,000 meters, and 1,250 meters. So I just did a multiple ring buffer here. I've introduced this concept already, so I'm not going to go into too much detail, but it's worth noting that we've got distances of 500, 1000, and 1250. Then we can convert the raster to the polygon, or the polygon to the raster, again, just like we did in the last model. But with this one, since we have more than one entity, it's important to note what we set the value field as. In this case, we're going to use distance because that's the value we're interested in. So we'll get a final output from this that is going to be essentially just distances from the water bodies layer, either less than 500, so that's either within, or 500 out, and then 500 to 1,000 and onwards. And then we can also say we're interested in multiple elevation scenarios. Say a tsunami of 5 meters, 10 meters, or 15 meters. So we could rank them with 10 to 15 being the most catastrophic, so it gets a score of 3. 0 to 5 being the smallest, so it gets a score of 1. And then we can simply add those two together using the Raster Calculator function, and we get a pretty simple risk classification metric for tsunamis, where we've got 500 in sets 1, 2, and 3, so that's within 500 meters, the various elevation thresholds, within 1,000 meters, the various elevation thresholds, and then above that. So this is just a pretty simplified analysis, but it's to give you an idea of how you can overlay multiple pieces of information. And I also hope today's lecture really highlights the benefit of, one, using Model Builder, but more importantly than that, just using some sort of visual representation to represent your workflow. You don't necessarily have to use Model Builder to do things, but it's nice to have some sort of graphic that can illustrate the flow of information through both your model and your thought process so that you can kind of justify and explain things down the line.